Hello, everyone, and welcome back after lunch. I'm just going to kind of, well, not waffle too much for a few minutes, but I think we've still got a few people turning back up. So we will have a nice, gentle reintroduction after your break. Hope everyone got on okay with the exercise before lunch. I think I did slightly underestimate how long that would take, so I do apologize for that. I think as long as you got through and ideally managed to make at least a confusion matrix, which was the most exciting new part, and maybe try out a random forest, then hopefully you got something out of your exercise, and the main goal was achieved. So what are we going to cover this afternoon? We've got our heads hopefully roughly around decision trees and random forests. But we do know that both of these model types are quite prone to overfitting. So are there any other more models out there that we might want to try instead? There are a couple of model algorithms that are extremely high performing. What we see a lot of when you go out and see what people are using out in the wild, whether that's in data science competitions or in published papers, we see a lot of use of things like LightGBM, XGBoost. Those are the kind of up there with deep learning networks in terms of what people are getting good performance out of. Now, XGBoost is the one we're going to primarily focus on today, but we're also going to touch on one called LightGBM and a couple of others, and they all belong to a family of classifiers known as boosting classifiers, particularly gradient boosting classifiers. There are a range of other variants like AdaBoost and CatBoost, and all of them have slight differences in how they operate, but they're kind of all fundamentally using the same underlying principle in how they build and use decision trees. And why do we bother teaching you about these classifiers? Well, they work very well on tabular data, which we tend to have a lot of in health, policing, social care, and public health. You can use them for images and the like as well, but neural networks tend to be what performs really fantastically there and on other unstructured data, particularly where there's very large data sets. XGBoost and the boosting classifiers can be used for classification or regression problems. So are we predicting a class label, or are we predicting some sort of continuous value, like whether the overall cost that someone might have to the health system within a particular period of time, or their length of stay, something like that. The other thing about XGBoost and the boosting classifiers, they often cope reasonably well with slightly smaller data sets. So the key thing that connects all of these boosting models that we're talking about today is you train weak learners, so they're quite shallow decision trees. These can sometimes be called what's a decision stump, so you just have one split. They're incredibly simplistic learners, but they can also be deeper depending on the exact algorithm we use and the parameters that are set. Main thing is you train these trees in sequence. Each tree is correcting the mistakes of the previous tree. So in some way, by focusing on the data points that the previous models misclassified, you can start to build a really powerful model that's incredibly good at predicting. Now, how does this differ from random forests? Well, they're both using multiple trees, but they're using multiple trees in a slightly different way. So random forests train multiple models independently, entirely independently. They're training up in parallel. The trees don't know anything about each other. They take the class that most of the models predict to be the final prediction. So if you've got 3 trees, 2 of them come to the conclusion that the sample you passed in indicates someone has the disease, and one of them indicates they don't have the disease, then the majority vote is going to be that that sample has the disease. In contrast, XGBoost is training multiple models one after the other to make one sort of final good prediction. So I've tried to split this up a little bit into the kind of key concepts and the bonus bits that might be interesting to you. So don't worry too much if you don't get the exact details of how XGBoost is working. Fundamentally, you want to understand kind of that it's adding together these multiple trees, correcting the mistakes of the previous tree in some way. So to go a little bit more in detail about how XGBoost specifically works, and XGBoost I'm choosing because it is the kind of the best one. It's a very, very popular one. It still works incredibly well. It's still being actively developed. It's what Mike in the stroke team recommends above all else, for example, from his real world experience using it on large scale health models, and finds it to be very good in that role. So XGBoost We're training a weak learner and we're seeing how it performs using some kind of loss function. Now, a loss function is just some way of measuring the error. When we minimize the error, we're trying to minimize the loss function. The loss function we choose is depending on the type of problem. We can adjust this in XGBoost parameters. If the loss function is higher, that generally means the prediction was worse. Now, XGBoost doesn't just look at the loss parameter, but it also incorporates some extra regularization terms to avoid the model becoming too complex, to avoid this overfitting problem. So XGBoost, on top of being very good at predicting, is also trying to minimize that impact of it getting too well fitted to the training data and generalizing poorly. So we've calculated the error. We're then trying to train a second tree that is using the original features, but instead of trying to predict the class this time, it's trying to predict the errors that came from the first tree. So each time we add the prediction from the first tree and when we add that to this tree, this should give us a better result overall, a smaller loss, a smaller error than just using the first tree by itself. Now, we use the gradient of the loss function to help indicate the way to adjust the model. Don't worry about this bit, this is just the bonus. The predictions from the subsequent trees are also added to the original predictions, but we scale them by something called a learning rate. Learning rates tend to be very small numbers. So all this means is each subsequent tree is making a very small contribution to the final prediction, and we're not overshooting the best prediction by learning too quickly, by making too big an adjustment at any one step. So we just keep repeating this process until we reach generally a certain number of trees. So we just keep calculating the error, training a tree to predict those errors, calculating the error, and keep refining and refining the prediction that we're coming to. We can also use something called an early stopping criteria. So if the performance stops improving for lots of steps in a row, or a certain number of steps in a row, however many we define, we stop the model from training further. And this is another way to prevent the overfitting taking place. The final prediction takes into account the prediction of all of the trees. So if the predictions, for example, if we're predicting a class sum to 0.6, we'll predict the positive class. If they sum to 0.3, we'll predict the negative class. Again, like we were doing in the logistic regression, we can change the threshold point to make sure we have that balance that's optimal for our use case of true positives and true negatives, effectively. That we want to balance its predictive power on what matters to us, thinking back to those ROC curves. So in summary, we're training weak, shallow trees. We're looking at how wrong they are. We're training another weak tree, but it's trying to predict the errors from the previous tree. We look at how wrong it is now, train another weak tree, and we keep repeating and repeating. What we get at the end is a model that tends to perform better than logistic regression, decision trees, or random forests. They tend to be very powerful predictors. So I don't think you're going to be too surprised to hear that the XGBoost model is actually very similar to the code we've been using all throughout the day. It's very easy to implement and very easy to slot into the code we've already been doing. So divide the data into features and inputs, training and test sets, optional k-fold validation, apply feature scaling. Well, no, we don't have to do that either. We're still in the realm of tree-based models, so we can just pass in our unscaled data. This time we're going to create an XGBoost model. I'm going to fit the model to our training data, just like before, predict Y from X in our training and test, and assess the performance of the model with all of the techniques that we've been building up to so far. So I'm going to skip over this because it's identical. We're going to split into the training and testing data, create this random forest classifier, not a random forest, so that should say an XGBoost classifier. So we are using a different library. That's the main thing to note here. We are importing from xgboost.sklearn the XGB classifier. Then all that happens is we create XGB classifier like this. And as before, remember, we don't actually need to assign back to model here. That's an error in the slides, but it won't cause a problem, it seems, if you do. So we are creating this XGBoost classifier using the XGBoost library, and XGBoost and their developers very kindly developed there is a way of using XGBoost outside of sklearn, but it fits very nicely into sklearn and all of the code that we've been using if you import XGB classifier from XGBoost sklearn. And that makes it very easy to therefore try out lots of different models as we've been doing. Going to predict the labels for our training and testing data, view the accuracy, all like before. So you can see there's hardly a single change to suddenly massively jump up your performance. Now, As I say, XGBoost is a very solid choice. And hot off the press from Mike today, we've heard about how it's actually incorporating aspects of LightGBM, which we're going to talk about in a minute as well. So it's getting more and more powerful. It's being actively developed. But I think it's worth telling you about the other boosted models that you may want to consider using, just so when you come across them in the wild as well, you kind of know what they're doing and how they're slightly different and why they might be useful for certain data sets. But before I talk about the benefits and disadvantages of each of those, I'm going to talk a bit more about why XGBoost is so good. Why does it do such a good job out of all of the models that we've got available to us? So XGBoost, gradient boosted models, these weren't new. XGBoost wasn't the first to do this, but XGBoost is designed to be incredibly scalable and incredibly computationally efficient. This allows you to use it on very large data sets. It can also be run in parallel. So on your computer, you most likely have a processor with multiple threads. In a lot of machine learning and a lot of code in general, it will only be using one of those at a time. But because of the way XGBoost builds trees, it won't be building the separate trees. Obviously, it needs to kind of correct the previous tree, but because of the way the trees grow, it can be training different arms of the trees as they grow in parallel, which can speed up training even more. And XGBoost incorporates ways of doing that. It can even be parallelized across multiple computers if you're working in a high-performance computing environment. And that's sometimes necessary for incredibly big and complicated models. Now, XGBoost uses regularization techniques as standard to improve the generalizability of the model. I'm not going to go into details of what they are, but if you're interested in reading more, you want to look at L1, which is called lasso regularization. That's a horrible word to say multiple times, and L2, which is called ridge. There's plenty of really good articles about this on the internet, so you can understand what these techniques are and where else they're used as well. XGBoost is also really good at handling missing data without you having to do additional pre-processing like mean imputation. So mean imputation is where you look at the average of a column and apply that to the missing data. You replace your missing data points with that. So you say you have a column of ages with a couple of missing, you take the average of all of the data points you have and apply that. There's all sorts of different imputation techniques that you can use, and we will talk about that in the final session of this module. But XGBoost, you can actually ignore all that, and it will deal with missing data for you. You might still want to use some of those other techniques, but it's worth knowing that XGBoost by itself, you don't have to do that straight away. XGBoost also employs some additional pruning strategies behind the scenes, again, just trying to avoid this overcomplication of the model and making it more generalizable. I want to share a real-world XGBoost example from just the other day. So Zella King and the team at UCL, we have been using XGBoost to train a model on historic emergency department data. They are then using this to provide predictions of upcoming bed capacity requirements based on the people currently in the emergency department. Now, Zella's webinar is available on the NHSR YouTube channel. Really recommend having a watch of that if you're interested in hearing more about how you could translate this to a real-world problem. And she's also following up in the next couple of weeks with a more Python-focused webinar on this. So the first one is very much looking at the broad concepts and how they built the overall kind of how the model is going to work, and why they chose the models they did. The second one is a lot more about the Python code that they have used to implement it. Now, downsides of XGBoost, it's not very intuitive and explainable. At least it's not really very intuitive without additional help of things like SHAP, which is a library we're going to talk about in next week's session, which really helps to tease out what's going on behind the scenes, what features are important, both at a global level, so looking what's the model taking into account overall most of the time, and also on an individual level, and how do features interact with each other and so on. It really kind of lifts the lid on what is going on under the hood of the model. There's criticisms of those methods, and there's also black box, not very intuitive models is a criticism that can be applied to all of the variants of boosted trees we talk about. It's not unique to XGBoost. And to be honest, as we said, random forests kind of have the same problem. They're not necessarily that much more interpretable by themselves without additional techniques being applied. They can still be prone to overfitting as well. XGBoost, hyperparameter tuning, all these parameters that we can tweak can help with this. The defaults are often quite good to start out with, but you will probably need to do some tuning. And you do still need to pre-process your categorical features. So things like, you know, when we were talking earlier about music genre, instead of having a column called genre with musical, rock, pop, musical, rock, you want to almost kind of flip this so it's a wide column, and you have a column for genre. Is, you know, is it a musical? Is it a rock? Is it a pop? And kind of true or false, or zeros and ones in there. So you still need to do that with XGBoost. There are some experimental features appearing in the library to avoid this need, but they are still experimental at this time. So how can we tune these models? Well, there are a large number of different parameters available. So there's things like the learning rate. Remember, we talked about, or I've briefly talked about this when we're looking at how XGBoost is trained. We have this learning rate to make sure it doesn't learn too fast and overshoot the best possible outputs, the best possible model. You can tweak that. It will make, you might make the model learn slower, but it might help it prevent to overfit. It might help it prevent going past the optimal solution. Maximum depth, same as before, same as our random forest, same as our decision trees. We can change the maximum depth of a single tree, and just like before, higher is more likely to overfit and it will start to use a huge amount of memory. Lower is more likely to underfit, to not capture all the complexity in the training set. There are a couple of additional parameters you might want to play around with. Larger values of these tend to make the trees less complex. They avoid creating very overfitted models. Lambda parameter relates to the L2 regularization. Alpha relates to the L1 regularization. Again, you might just, if you're interested in tweaking these parameters, I'd recommend going away and reading the documentation, reading up about these, just to understand what that's doing and why. And then subsampling, which is when this is set to less than 1, this subsamples the proportion of the data for the next boosting round. So again, we're adding in this randomization element that can help to reduce this overfitting. So that's sounding like quite a lot of parameters to try out, isn't it? How on earth am I ever going to work out the best possible combination of all of these? I'm not going to tell you how to do that today, but in session 4J, the last one of this module, we're going to talk about things like grid search and an optimization framework called OpTuner that can help answer those problems. So for now, I'm just going to recommend trying out some different combinations, but in those sessions, we will have more structured ways to answer that question for you. Now, there are lots of variants on boosted trees. As I said, XGBoost does remain very popular, and I would recommend it probably as your first port of call, but the other options may work better on your particular data set. And just like XGBoost, most of them slot very neatly into our existing code. So the first one I'm going to tell you about is AdaBoost. It's adaptive boosting. Now, what this does is train a large number of weak classifiers sequentially, just like before. These do tend to be these decision stumps, these incredibly shallow trees, you know, maybe only one split when we're working with AdaBoost. After each round, what it is doing is paying more attention to the instances where it previously got things wrong. It weights the samples where it previously made a bad decision. So it is using boosting, it's not using what's called gradient boosting. It then takes a majority vote from all of the classifiers to make the final prediction. So it is actually kind of developing these separate trees, a bit more like random forest. It's kind of this weird middle ground between the two almost. It's taking this majority vote, but by weighting the instances where it made bad predictions previously, it can start to work towards this better final output, more so than just random forest alone. It's not really used that much anymore. XGBoost is generally a better option. AdaBoost is quite sensitive to the noisier data and outliers because of the way it focuses on these tricky examples, which may not be that representative. It doesn't have many tunable parameters in comparison as well. Could be a bad thing or a good thing, depending on how you look at it, but it can fail to capture these more complex patterns in the data set that XGBoost is better at picking up. What I'm going to do is mention it just so you know when you come across it that maybe it's not one that you're so interested in trying out, but it's worth knowing it's there. It's included in sklearn, which is quite nice. You don't have to go and get an extra library. From sklearn.ensemble, which is where we also imported our random forest from, we're going to import the AdaBoost classifier and set up just like before. Now, CatBoost is another type of boosting model. This one is particularly good with categorical data, and it avoids this need for categorical encoding that we've been talking about. It was developed in 2017, so still quite recent, made open source in 2019. All of these have really come about since, I think, about 2016 onwards, so they're still relatively new. Some of them are even newer than that. CatBoost, like I say, unlike decision trees, random forest, XGBoost, AdaBoost, you don't have to do so much manual pre-processing of the categorical data. So it's quicker to set it up, and it has some clever tricks for dealing with categorical data that mean it performs quite well on categorical data, which we do tend to have a lot of in health and health, social, and policing. It's also designed to work really well out of the box. So it's a little less prone to overfitting than XGBoost when you don't set any of the additional parameters, when you just set the defaults. You may need to spend less time tuning, therefore, than with the hyperparameters compared to XGBoost. But as a trade-off, it may not be quite as fast as some of the other boosted trees are. But again, very simply, this time we're using the CatBoost library. So we've installed as part of our environment the CatBoost library, importing the CatBoost classifier, training it just as before. Now, when you start training on very large data sets with any of these, training can be extremely slow, particularly if you have lots of continuous variables. So these are things like, maybe you have blood pressure, maybe you have height, maybe you have weight, maybe you have all sorts of different kind of test results that were returned as a numeric value of some kind. Now, histogram boosting models bin the continuous variables into ranges, and this can really help speed up the model fitting process without sacrificing accuracy particularly. So let's imagine we've got a continuous variable with lots of different clients. Here I've just chucked it onto a random bar chart just showing the values of each individual client. What we can do instead is put this into ranges. So let's say that we've gone, client 1 we've looked at and gone, right, let's put this into the category 1 to 9. Client 3, yeah, you also fit into 1 to 9. Client 2 fits in there. Client 3, 10 to 19. Client 4, right, 30 to 39. And so we're starting to build up fewer things that it has to sort of look through and work out the best split points for. It makes it much quicker and simpler for the model to work out those different splits rather than having to evaluate quite as many possible split points as before. So we can either use sklearn's own histogram gradient boosting classifier. So that's again from sklearn ensemble. And we just import that. So that's where we found random forest, is where we found AdaBoost. We import the histogram gradient boosting classifier. Now, finally, we're on to LightGBM, light gradient boosting machine, I think. So this was developed specifically by Microsoft, and that might be why some of you who are working on Macs had a little bit of difficulty with getting it to install. I suspect it has been neglected somewhat on the Mac side of things. But they have recently rectified that, as in within the last 3 weeks or so, they've made it slightly easier to install. It uses a slightly different way of growing the trees to XGBoost, and this can make it less memory intensive. This can alter the speed at which it can train, and it uses this histogram-based splitting. That's one of its big things. One of its big benefits for speed and efficiency is that it was one of the first ones to really incorporate that histogram-based splitting. So LightGBM as well, like CatBoost, you don't have to undertake one-hop encoding. Like XGBoost, it incorporates the L1 and L2 regularization to help with that generalizability of the model, and it has all sorts of other features that just make it efficient. It's, again, as well, not quite as sensitive to the hyperparameters as XGBoost is, so it might work better out of the box than XGBoost. It might be less prone to overfitting with the default parameters, and you might not have to spend so much time fiddling with it to get a good model. It generally works very well straight away. And again, this time you're just importing from the LightGBM library the LGBM classifier. So just like in our random forest, there is a certain level of randomness in these models. To make our models reproducible, again, we should always be using this random state parameter in all of these, both for our train test split and when initializing each of these models. So last thing I'm going to say on that, because I forgot to say at the time, is that just coming back to a LightGBM, as I say, hot off the press from Mike today, XGBoost is starting to incorporate some of this histogram-based splitting as well. So that might only be in the most recent builds. I'm not sure on that one. It sounds like it's a new parameter that you can set when initializing the model. I did see come through in the chat that unfortunately, Yeah, I completely agree with you when the XGBoost documentation is horrible. It's really not very nice to read. It's a little bit confusing, especially because XGBoost kind of works across the command line. It works in Python, it works in R. It's a little bit difficult sometimes to work out which parameters you can use and which you can't. So that is one of its downsides. But overall, you will find it useful to it's useful to know that that's on the horizon and maybe something you want to try out. It may make some of these other models obsolete. We'll see. Now, a couple of other classification algorithms that are completely different that I just kind of want to let you know exist. We're not going to go into detail about them on this course, but you will probably come across them when you're exploring sklearn, when you're reading general machine learning papers, etc. So k-nearest neighbors is a classification model that looks at the data points nearest to it and that are most similar. Now, nearest becomes very complex when you start looking at high dimensional data. So we're just going to think about it in quite a simple manner here. But effectively, let's think about this green circle here. We don't know what class this belongs to. Should we classify it as blue squares or should we classify it as red triangles? Now, depending on what points we look at nearest to it. So let's say we want to look at the two nearest points to decide our classification. Well, we'd classify it as a red triangle. If we based it on the three nearest points, we would still classify it as a red triangle, but we'd have a little bit of uncertainty because it could be a blue square, but the majority of points within that range are a red triangle. And then finally, based on the nearest five, well, actually, then we're starting to find that our nearest are the blue squares. So actually, three of our near instances are blue squares, two of them are red triangles, and so on. So you're kind of just looking at this similarity of each data point to other data points in your historical data set. Now, you do need to scale and normalize when you're doing this model. There is a weighted variant that can overcome issues with data imbalance. You can just import this from within sklearn as well if you're interested. There is I'd recommend going to the sklearn documentation. Techniques exist to help select what k should be. So, where we're saying, should we look at the two nearest, the three nearest, the four nearest, five nearest? There are plots and techniques that you can use to work out the optimal distance, effectively the optimal k value that you should be looking at. If your k is too large, you're going to have high variance, you're going to be underfitting, you're going to be looking, it's going to be too generalized, it's not going to be very well, it's not going to be very aware of small local patterns. However, if k is too small, if you're only looking at the very nearby values, then your overfitting is going to be, you're going to have a highly biased model. One thing to recommend as well is if you're working with a binary two-class classification problem, you want to make k odd to avoid ties. Otherwise, you can find yourself in a situation where you've got, the two nearest points are red triangles and four nearest points, you've got two red triangles, two squares, let's imagine, and then that can cause issues because how do you say whether, which class you should choose if you've got a perfect 50-50 split between what the points could be? So that's worth bearing in mind. Other ones to be aware of, again, I'm not going to talk through these, but you may hear about support vector machines and you may hear about naive Bayes. These are also good models to consider. They're not tree-based, they're completely different, but you may want to go away and have a read about them if this is an area you're really interested in. And again, these are both available for implementations within sklearn, and there's a little bit here about how to actually initialize those models within sklearn if you want to try them out. So just here as well, we've got a summary of all the different classification models, when you might want to consider using them, and how you import them, which libraries you need to import them from. So how are we doing for time? So we're up to 2 o'clock. We're going to spend half an hour just trying out these additional models on our datasets from earlier. You can either open up your random forest stroke exercise that you were working on just before lunch and carry on from in there. Or if that notebook's feeling a little bit bloated, there is boostingexercise.ipy notebook available in the repository, which is just loading in the dataset and then leaving you to kind of do what you want with it. It just means if your notebook's starting to creak a little bit with all the plots, etc., you created earlier, then you may want to use that instead. If it's not, then carry on using the random forest stroke exercise. You've already got all the data imported, etc., and you can work within that. But what I want you to do is just spend a little bit of time trying out these additional models, seeing if you run into errors, seeing if you run into problems, seeing if you can try out some of the different parameters, seeing if you can go and have a look at the documentation. We're starting to sort of take the training wheels off here and give you a chance to look at how, if you're out in the real world starting to do your projects, your models, where you would need to go away and look up these additional parameters from the documentation. You might need to go and ask Stack Overflow, what additional things could I do, that's kind of thing. So just try tweaking the parameters, just have a bit of a play for half an hour, see what performance you can achieve. If you haven't already, I would really recommend trying to write a function to reduce how much code you're having to copy and paste each time you assess a model. Now, I'd probably recommend if your group hasn't already done this, do this at the start, just because it can make it a lot simpler. Rather than having to copy and paste loads of stuff, you can then just pass in a model and get all of your outputs very simply in one line of code, which can be very helpful when we want to compare different model parameters, etc. There is a example of this, a nice example of this in the Zilog PSG. There will be some points going out for that. But just, yeah, that would be my recommendation. Before we kick that out, before we kick off, then I will go through some of the questions. So the slide before this one, that one there, you may need to refresh. It may, because there's so many of you working on this or with this presentation open, it effectively may have not refreshed. I've recently moved that to because I thought it would be more useful here than when I had it where I had it originally a bit later in the slide deck. Optuner optimization part of hyperparameter tuning, yes it is. So Optuner is a framework that helps to automate the process of working out the best possible combinations of parameters that you might want to use in your models, and we'll cover that framework in the final session of this module. Asking a little bit about model libraries and which are the current state of the art. How's the best way to keep on top of what are these best and most state-of-the-art models? Some really good suggestions coming out there. Mailing lists and social media. Yep, I'd completely agree with that. I'm happy to share after today a couple of the newsletters and the like that I'm subscribed to. Podcasts, social media, as you say, LinkedIn. We're following some people on LinkedIn. People like I can't remember her name. There's a fantastic ex-Google person who talks a lot about, the cutting edge of data science. So I'll share some links, and it'd be great to maybe get a bit of a thread going on the Slack of any other links that people have got a recommendation to, any people that you find particularly useful. As Dan says, we also ask Mike. Mike is our resident machine learning expert. So we're always learning from what him and his team are doing on the stroke modelling projects and other similar projects like maternal health classification stuff that they're looking into. What have you been trying out recently? What have you been hearing about? What's performing well? What's on the horizon? And there's lots of things filtering through on things like model explainability and causality, working out more about what, not just is there a kind of link between, if this goes up, does this also seem to go up? Actually, what's causing that change? A little bit sort of more complex. So that's another big thing. Medium. So there's a thing called Towards Data Science. That's a kind of, it's a fairly crowdsourced, almost effectively publication. Anyone can submit to that publication, but I believe there's then a vetting process before the articles are published. But again, that's a very good way to find tutorials, find additional, notes and discussions about new libraries. So Medium's great, but you do a lot of the articles are behind a paywall. So you may find that, but you do occasionally come across good free ones, and I think Medium gives you a couple of free ones a month as well. Anything else? Just looking back as well, one-hot encoding, yep. So some people have given a nice brief overview of one-hot, but we will talk about this more this afternoon, and we'll go into a little bit more detail with some nice examples of what one-hot encoding is and how we move from data that isn't one-hot encoded to data that is. Large data, yep, there isn't really a strict definition, unfortunately. If your data set is so big that you can't actually store it all in your memory, that's kind of, yeah, a pretty good starting point. I don't have a particularly good kind of cutoff point for what big data is. We're probably starting to talk about hundreds of thousands to millions of rows in general. Just having a look a little bit further back. If there's any I haven't got to here, I will pop a note. I'll put together a troubleshooting, not troubleshooting, the frequently asked questions document. And yeah, I think that's probably best if I come back and just kind of address any of those afterwards. But I will set you off now. So we'll spend half an hour with just a bit of chance to try and write those functions, try play around, keep practicing your confusion matrices, your classification reports. Start thinking about how might you present this, how might you start to try and work out how to decide between these. Thinking about the fact that we're working with a model that is looking at classification of stroke and thrombolysis, what could be the downsides of models that have too many true false positives or false negatives. How might you want to balance it? How might you want to make your process of assessing your models more efficient? So just have a bit of time talking about this. In particular, try out XGBoost. That would be my top one to try out. And we will work on this for 30 minutes and we'll have a 10-minute break as well. So we will be back at 2:45. No, we won't. Yes, we will. We'll be back at 2:45. I will, and I will open up the breakout rooms now. Hi everyone. So I'm bringing you back now as originally planned, but I'm aware that groups are all at quite different points in that exercise. What I'd recommend is if you feel like you've got more to do on that exercise and you'd like to carry on, you were getting somewhere and you want to play around with those models a bit more, when we get to the next exercise, take the first, 20 minutes, half an hour to carry on with that exercise. That's absolutely fine. But for those groups that have got a little bit further and were kind of reaching the limits of your modification and playing around with different parameters, I want to give you the next exercise and the tools for the next exercise to be able to work on that. So a couple of other things that I just wanted to bring up as well, based on what I saw while I was going around the rooms. I believe we might have mentioned this briefly in one of the earlier machine learning sessions, but effectively, what is good practice and what we haven't been doing today, because we'll talk about it a bit more in a later session again, is rather than just having a training and testing split, we can also use things like k-fold validation, but we can also just use a train, validate, test split. So here, instead of us splitting our data set into 3 parts, we just split it into into 2 parts, we split it into 3. So instead of having 80% of our data as training and 20% as test, for example, we might split into 80% for training and 20% for test. We might then split our training data set further into a training data set and a validation data set. Now, the validation data set is what you would use when you are refining all of these model parameters, when you are tweaking things, when you are trying out the different hyperparameters and all of that. So that's good practice to then keep back your test data set to only use at the very, very end. It's a good way then to be sure that you're treating it like some real unseen data, rather than continually tweaking that performance to kind of try, to almost effectively just get better and better performance on a real world data set. Keeping the test data set back separately like that and using your validation data set in the way that we've kind of been using today is a better way to make sure that you don't accidentally start training or almost leaking the results of your training into your testing data set, and starting to almost train to the test data set. You know, that's a bad way to go about things, or it can be a problematic way to go about things. So train, validate, test can be a good way to avoid that problem. Other thing to mention as well, just a reminder, a bit of a warning about variable names, because I think in particular, the names of some of the functions we've used today are very tempting to also use as variable names, and this can really trip things up. So if you imported from sklearn metrics, for example, the F1 score, and then you created a variable, whether in your main code or within a function called F1 score, you may start to run into problems because it will overwrite. Potentially not so much within a function, but generally it's still kind of best avoided. So what you're effectively doing then is overwriting. The first time you run this code, it will run the F1 score function, and then it will create a variable that is called F1 score. That F1 score function no longer exists in your code. Effectively, it's been overwritten. Every time you then try to run F1 score on something else, it's just going, well, this is a variable. I don't know what to do with this. This is just a number that you've stored. I can't, I can't do anything with Y test and Y predicted test. That's useless to me. So that can really cause problems, and you can find yourself with some very obscure error messages that don't seem to make much sense. It's quite an easy way to lose a couple of hours debugging because you don't realize that you've somewhere overwritten this, and it can be a little bit confusing. So if you've done that, you'll want to go through and change your variable naming in some way. Maybe you want to call the variable something like F1 score calculated, just so that you can keep track of what it is. But you will then need to go back up to the beginning of your notebook and rerun your import statements. You will need to re-import the packages from the very beginning, because you need to kind of correct what your code environment thinks the F1 score is. And that can apply to, precision score, recall score. Those are all easy ones to accidentally overwrite. So just bear that in mind. You may need to change your variable naming and then rerun all of your code from the start.